Bismillahirrahmanirrahim. Today in our series of lecture of internal combustion engine, we will be studying chapter 6, that is fluid motion within the combustion chamber. Now, in last part of chapter 5, in our third part of chapter 5, we have studied this simple block diagram. Now I once again recap your knowledge. Let's see on the right side of this slide, we have a fuel system here. We have a fuel tank, fuel pump, fuel filter, and it is coming towards the carburetor that we have studied in chapter 4. Now, in chapter 5, we have studied about the air induction. We have atmospheric air. Air comes to the air filter. From air filter, it's cleaned and then it goes to the throttle body and then to the carburetor of old conventional vehicles. And in carburetor, these air and fuel mixture are made in appropriate ratio and then goes to the intake manifold. From that intake manifold, the air fuel mixture goes to the combustion chamber or the cylinder. And there, what happening now inside this combustion chamber or cylinder? Let's see. Now, air, fuel, and exhaust gas motions, it is important to have these motions to speed up evaporation of the fuel. We will talk about air and fuel for exhaust. When we will study chapter of combustion and exhaust, we will cover this portion. So at the moment, we are only focusing on air fuel, which is going inside the combustion chamber. So it is necessary. Why it is necessary or it is important? It's to speed up evaporation of the fuel, enhance air fuel mixing, increase combustion speed and efficiency. Now, we require some turbulence there. But why turbulence? Due to the high velocities involved, because as we have seen in chapter 5, at the inlet, the speed of the sound, the intake, the pressure differential, and these pressure waves are generated, and the speed of that inflow is equivalent to the speed of the sound or ratio of the speed of the sound. So due to the high velocities involved, all flows into, out of, and within the engine cylinder are turbulent flows. So high speed velocities are there, and due to high speed velocities, all flow which is going in or out or within the cylinder are turbulent flows. So thermodynamic transfer rates within the engine are increased by an order of magnitude if we have that turbulence flow. Heat transfer, evaporation, mixing, and combustion rates all increases due to this turbulence phenomena. Now, when a flow is turbulent, particles experience random fluctuation in motion superimposed on their main bulk velocity. Now, when your fluid is flowing in a turbulent phase, okay, the speed is in turbulent range. The particle experience random fluctuation in the motion superimposed on their main bulk velocity. These fluctuations occur in all directions, 360-degree, perpendicular to the flow and in the flow direction, so in all directions. This makes it possible to predict the exact flow conditions at any given time and position. Now, turbulence, we can divide the level of turbulence within an engine, large-scale turbulence and small-scale turbulence. Now, let's see the small-scale turbulence. Totally random and homogeneous, the small-scale turbulences, no directionality and controlled by viscous dissipation. Now, in case of large-scale turbulence, that occurs with eddies on the order of the size of the flow passage. So it occurs with the eddies on the orders of the size of the flow passage. Fluctuations are random but have a directionality controlled by the passage of the flow because they are in closed environment. So we have this characteristics. Now, types of motion of air fuel mixture. During the intake stroke, normal desired turbulence is required. A rotational motion called swirl is generated. During the intake stroke, we require normal desired turbulence. and that rotational motion is called as swirl. Okay. Near the end of the compression stroke, we have a squish. Squish is the radial motions towards the center or line of the cylinder. So the motion of the molecules of the air-fuel mixture, which is coming from outer periphery to the inner center line of the cylinder, that motion is known as squish, is the radial motion towards the center line of the cylinder. Tumble. Tumble is the rotational motion around a circumferential axis when we have a very closed volume. Only when we have a clearance volume near to the clearance volume, then we have this tumble mass, okay, motion. Then during compression and combustion, crevices flow. This is the flow into a very small crevices of the combustion chamber due to the very high pressure. There are a lot of crevices in your combustion chamber. These crevices are maybe in the head and the body between the gasket, or where you have placed the spark plug or the fuel injector, or between the piston walls and the cylinder wall. You have some opening or gaps. Those gaps are known as crevices. Then we have a blowby. Blowby is the escaping of the gases from the combustion chamber to the crankcase from the piston valves and the cylinder walls. In between there is a gap, and the gases during the combustion, after the combustion, those escapes from that portion on from that the cylinder wall and the piston walls gap, is that escaping of the gases is known as blowby. Now, turbulence intensity as a function of engine speed. On x-axis, we have engine RPM, and on y-axis, we have turbulence intensity. At whenever we have a less speed or speed is low, turbulence intensity is low. The more the speed is, more the turbulence intensity is. So they are directly proportional. Now, swirl, the first and the most common motion which is happening inside the cylinder is the swirl. The main macro mass motion within the cylinder is a rotational motion called swirl. It is generated by the construction of the intake system to give a tangential component to the intake flow as it enters the cylinder. So it is natural, and sometimes it is generated, and it is generated by the construction of the intake system. Intake system here includes your intake manifold, then the designing of the intake valve, all these construction of that intake systems to give a tangential component to intake flow as it enters the cylinder. This is done by shaping and contouring the intake manifold. This swirl motion we achieve by shaping and contouring the intake manifold, valves, ports, and sometimes even the piston face. The top of the piston face is sometimes is made like that we should have a swirl motion of the air-fuel mixture which is coming in. Swirl greatly enhances the mixing of the air and fuels to give homogeneous mixture in a very short time. Available for this in modern high-speed engine. In modern high-speed engine, the speed of the piston is very high. Okay, when speed is very high, it has a very short interval of time for mixing of air and fuel. So swirl greatly enhances the mixing of air and fuel to give homogeneous mixture in the very short time available for this in the modern high-speed engines. It is also main mechanism for very rapid spreading of the flame front during the combustion process. So due to this swirl action, the spreading of the flame front in the combustion rapidly is happening because of the swirl motion. Now, method to generate swirl. First, swirl motion within the cylinder is like this. This is your intake manifold, and the air is swirl in this piston is going down, creating a vacuum, and the air is coming from this intake manifold, and we are having a swirl motion. Second, you have designed the valve in like this, and air intake is like this. So air entering the cylinder from a tangential direction. So it is a tangential direction. Or in the third case, if you make the contour intake runner, you make a contour and the air is already swirling in this, or you made the walls like geometry, walls shaped like this, that they produce some swirl action here. So these are the four methods in which by which you can produce swirl inside the combustion chamber or the cylinder. Now, swirl ratio is a dimensionless parameter used to quantify rotational motion within the cylinder. Swirl ratio is a dimensional parameter used to quantify rotational motion within the cylinder. It is defined in two different ways in the technical literature. One is when we have swirl ratio. One, the angular speed divided by the engine speed. So angular speed divided by the engine speed. Number two, swirl ratio, swirl tangential speed divided by average piston speed, UT divided by UP bar. So average value of either the angular speed or tangential speed should be used in these equations. So we will use the average value of the angular speed or the tangential speed, swirl tangential speed in these equations. Angular motion is very non-uniform within the cylinder, being a maximum away from the walls and being much less nearer the wall due to viscous drag. So this is the reason. The non-uniformity is both in the radial direction due to drag with the cylinder walls and in the axial direction due to drag with the piston face and the cylinder. So this non-uniformity is due to the radial direction. Non-uniformity is both in the radial direction and in the axial direction. In radial direction, it is due to the drag of the cylinder walls, and in axial direction, it is drag with the piston face and the cylinder head. Now let's see this example, this figure. Figure 6-3, average cylinder swirl ratio as a function of crank angle for typical SI engine. Swirl is high during the intake process. With the maximum near the TDC, it is then reduced by viscous drag during the compression stroke. There is a second maximum near the end of the compression, and the radius of the rotation is increased during decreased near the TDC, and the expansion from the combustion occur. Viscous drags with the cylinder walls during the expansion stroke quickly reduces this again before blowdown occurs. So now your piston is at TDC, we have a high amount of swirl motion here. As the piston goes to the BDC, this area is increasing and swirl ratio is decreasing. Now piston is at BDC, still decreasing, the swirl ratio is decreasing. Now somewhere before TDC in the compression stroke, it's minimum. Okay. Then we have some ignition before the TDC, and then we have the combustion. So just after the TDC, the swirl ratio increases because the swirl ratio is the main source of this flame propagation in the combustion chamber. So we have a squish moment, and at the end we have a tumble here, and then swirl motion is increased. And then in the power stroke, the area is increasing and it is decreasing. So it is like this with crank angle. Now, geometry of the piston and the cylinder is also an important factor. Now, the combustion chamber geometry of the modern automobile engine with most of the clearance volume near the center line of the cylinder. So this is the center line of your cylinder. This is your piston. This is the clearance volume, and this is the cylinder head. So this is your center line in most of the modern vehicle automobile engine. The most of the clearance is near the center line of the cylinder. This increases squish and tumble and decreases the flame travel distance for most of the combustion process. So this increase in clearance near the center line decreases the flame travel distance for most of the combustion process. Engine can be built with the clearance volume in the cylinder head. So this clearance volume in the cylinder head is increased, or as a bowl in the crown of the piston face, or as a combination of these. So we have a piston head like this, and we have a crown here too, but here we do not have the clearance volume in the cylinder head, and the clearance volume is in the piston head. So the crown of the piston face, or as a combination of both these two. So we can have this type of geometry in our modern vehicles. In two-stroke cycles, engine with intake ports in the cylinder walls, swirl is generated by shaping the edge of the ports and direction of the intake runner. We have in two-stroke engine, we have ports, and we design the ports and we give some angle there. So when we give some angle, the air is coming. We are producing swirl at the entrance with that port shaping of the edges and the port and direction of the intake runners. Swirl greatly reduce dead spots in the scavenging process. Swirl is the function that is one of the function is that it greatly reduces the dead spots in the scavenging process, but also increasing the mixing of the inlet charge with the exhaust residue. So in two-stroke engine, so it's like this. The shaping of the inlet port and the runners to promote swirl reduces the volumetric efficiency of the engine in all cases, whether it's an SI engine or it's a CI engine. For a CI engine, the period of one swirl rotation and the number of holes in the injector nozzle should be related to injection time. So for CI engine, we mostly use injector nozzles. So the relationship is in CI engines, the period of one swirl rotation and the number of holes in the injector nozzle should be related to the injection time, as injection time is equal to period of swirl divided by the number of holes. So this is the relationship. This will assure fuel distribution throughout the entire combustion chamber as shown in figure 6-5. Now squish and tumble. When the piston approaches TDC at the end of the compression stroke, here in this figure, piston is compression stroke. When the piston approaches TDC at the end of the compression stroke, the volume around the outer edges of the combustion chamber is suddenly reduced. So the volume around the outer edges of the combustion chamber is suddenly reduced to a very small value. Many modern combustion chamber design have most of the clearance volume near the center line of the cylinder, as we have already discussed. Many modern combustion chamber designs have most of the clearance volume near the center line of the cylinder. As the piston approaches TDC, the gas mixture occupy the volume at the outer radius of the cylinder is forced radially as this outer volume is reduced to near zero. So the volume or the space available when the piston is reaching TDC is available at the center line. At the center line, it may be in your piston head, or it may be on the bowl of the piston. Maybe the bowl of the piston head or in the head where we have a maximum clearance. This radial inward motion of the gas mixture is called squish. Now, it adds to other mass motion within the cylinder to mix with the air and the fuel and quickly spread the flame front. Maximum squish velocity usually occur at about 10 degrees before TDC, as we have seen in that figure, that maximum squish is happening before 10 degree VDC TDC. Maximum squish velocity usually occur at about 10 degrees before TDC. As the piston approaches TDC, squish motion generates a secondary rotational flow called tumble. So as the piston approaches TDC, squish motion generates a secondary rotational flow called tumble. This rotation occurs about a circumferential axis near the outer edge of the piston bowl, like this. So this rotation occurs about the circumferential axis near the outer edge of the piston bowl. Tumble action caused by the squish as piston approaches TDC. So this happening here. Tumble is the rotational motion about the circumferential axis near the edge of the clearance volume in the piston bowl or in the cylinder head. So during the combustion, the expansion stroke, begins and the volume of the combustion chamber increases as the piston is moving from TDC to BDC. As the piston moves away from TDC, the burning gases are propelled radially outward. So they will be moving like this, okay, to fill the now increasing outer volume along the cylinder walls. This reverse squish helps to spread the flame front during the later part of the combustion. So once again, I repeat this point. During combustion, your combustion starts before TDC, and during combustion, when piston reaches TDC, your combustion had already started. The expansion stroke means when your piston is moving from TDC to BDC begins and the volume of the combustion chamber increases. So piston is moving from TDC to BDC. The volume area is increasing in the combustion chamber. As the piston moves away from the TDC, the burning gases are propelled radially outward to fill the new increasing outer volume along the cylinder wall. So piston is moving down. We are having more volume to fill that volume. That flame propagation, that combustion gases has to occupy that area. This reverse squish helps to spread the flame front during the later part of the combustion. So this is the reverse squish. We have stated this. Now, another thing, divided combustion chambers. Some engines have divided combustion chambers, usually with about 80% of the clearance volume in the main chamber above the piston and 20% of the volume as the secondary chamber connected through small orifice. So in some cases, we have this divided combustion chamber that is usually the 80% of the clearance volume in the main chamber and above the piston and 20% of the volume, that clearance volume, as a secondary chamber connected through a small orifice. Let's see. We have like this is your cylinder and this is your cylinder. This is your piston and this is your main chamber. Okay. And this is your, from this portion to portion is secondary chamber. In this, its main chamber comprises of 80% of the clearance volume and this secondary chamber here from that in this portion occupies the 20% of the clearance volume. So combustion is started in the small secondary chamber and the flame then passes through the orifice where it ignites the main chamber. In the secondary chamber, as we have seen, we have a spark plug. Okay, so we get a spark here and we have a ignition and combustion here, and the combustion developed in this region. Now, combustion is started in the small secondary chamber and the flame then passes through the orifice where it ignites the main chamber. So the flame is coming from this orifice and we have airflow mixture here that is 80% of that clearance volume and it ignites that airflow mixture here. Intake swirl is not as important in the main chamber of this type of engine, so the intake system can be designed for greater volumetric efficiency. Now, the intake swirl is not important if we have this divided combustion chamber type of a cylinder, because in the main chamber of this type of engine, so the intake system can be designed for greater volumetric efficiency. Now let's read this figure 6-7. Divided combustion chamber of an SI engine. Secondary chamber will typically contain 20% of the total clearance volume. So 20% is of the total clearance volume is like this, and 80% of the clearance volume is in the main chamber. Combustion is generally initiated in the secondary chamber by positioning of the spark plug, because we have placed the spark plug here. So the combustion will be initiated here. The main air-fuel mixture in the primary chamber is ignited by torch ignition. Because of this orifice, we have this torch ignition. As the flame expands through the orifice between the chambers, often divided combustion chamber engines are also stratified charge engines. We will study when we will study the next chapter what is stratified charge engine. With a rich charge in the secondary chamber for good ignition and lean charge in the primary chamber for good fuel economy. So we may maintain lean and good mixture like this. Now, it is desirable to have very high swirl in the secondary chamber, and the orifice between the chamber is shaped to supply this. Often the secondary chamber is called the swirl chamber. Now this divided combustion chamber, it is desirable to have very high swirl in the secondary chamber, and the orifice between the chamber is shaped to supply this. Often the secondary chamber is called the swirl chamber. As the gases in the secondary chamber are consumed by combustion, the pressure rises and the flaming gases expands back through the orifice and act as torch ignition for the main chamber. The expanding gas rushing back through the orifice creates a large secondary swirl in the main chamber, which enhances the combustion there. Now, the next part after the combustion, then we have the crevices flow and the blowby. In the combustion chamber of an engine, there are tiny crevices. The crevices mean gaps that fills with air, fuel, and exhaust gases during the engine cycle. These crevices includes the clearance between the piston and the piston walls, about 80% of total. As you see, this is your wall of the cylinder. Okay, this is the wall of the cylinder, and this is your piston. So this gap between, we have a crevice here. This is a gap. These are the gaps between the piston wall and the cylinder walls. So the clearance between the piston and the cylinder wall, about 80% of total. Imperfect fit in the thread of the spark plug or fuel injectors. So if we have placed this spark plug or fuel injector in the head, so due to that imperfect fit in the threads of the spark plug or fuel injector, we have 5% of the clearance volume there. Crevices volume. Gaps in the gasket between the head and the block, 10 to 15%. Remember, in our first chapter, we have seen the head on the top, and then we have an engine block. And to fasten both these two metal metal parts or metal surfaces, we must have a gasket. Whenever we have to couple or fasten two metal portion, we need to have some gasket in between. And that gaps in the gaskets causes 10 to 15% of that crevices area. Unrounded corner at the edge of the combustion chamber and around the edge of the wall faces. So some few volume percent unrounded corner at the edge of the combustion chamber and around the edge of the wall faces. Although this crevices volume or this gap volume is on the order of only 1 to 3% of the total clearance volume. So clearance volume is already very less, and this crevice volume or gap volume is 1 to 3% of the total clearance volume. So very, very less. The flow into and out of it greatly affects the overall cycle of the engine. But this 1 to 3% of the total clearance volume, the crevice volume or the gap volume, greatly affects the overall cycle of the engine. Now, let's see how blowby occurs when combustion chamber gases are forced past the compression ring of the piston. Let's see in this condition, when your piston is moving up from BDC to TDC. These are the compression rings and this is the oil scrap ring. So we assume that we have a piston which have two compression ring. This is the groove in which you have the rings mounted, and this is the groove for the oil ring, and this is your piston with connecting rod here with the wrist pin or the connecting pin here, and these are the cylinders walls. Now piston is moving from BDC to TDC. At that time, your rings will rest on the lower surface of the piston walls or piston grooves. Okay, so the gases, now you have a combustion here, gases will come in this area. So the gases which are here and here will come in this area. Okay, similarly Now, when piston is moving from TDC to VDC, when piston is moving from in right figure, the grooves we have, the rings will try to rest on this upper surface of this groove. So the gas which are already trapped here will come from this area and will entrap here, and the gas which are already there will come from this area and entrap here, and gas here, here in this area, and will come to this area, and this it will goes to your crankcase. Okay, so let's see. As the piston moves up the compression stroke, the compression rings are forced to the bottom of the ring grooves, and the gas is forced into the crevices, volume between the piston and the cylinder walls, and into the piston ring grooves. Now, when the piston reverse direction for the power stroke, the piston rings are forced to the top of the groove, and the gas in the grooves can flow past the piston. Gas also leak past the piston rings through the gaps where the ends meet. So one area is the passage is this from where your gases are going, okay, down. One is this. One is the gap between the piston ring where it ends meet. Let's see. So various design used on the end of the piston ring. So this is the gap here from where gases can escape, okay, or in this shape, or in this shape like this, or from this shape. So now, due to the shape of the piston and this gap is known as butt gap, BUTT, butt gap. Butt gap is the gap between the piston rings when placed in a cylinder. That gap is known as butt gap. It has to be minimized. So there should be no passage for the compressed gases or the exhaust gases or the residues to pass through the piston. So one was this area and one was this area, and second was this. The most commonly rings which are used in the modern automobile engine is this E-type. So these are the two portions or two areas from there the compressed gases or the exhaust gases escape, and this is known as this process escaping of the gases from the combustion chamber to the crankcase is known as blowby. The gas that gets totally past the piston and ends up in the crankcase is called blowby. Late in the power stroke, when the exhaust valves open, late in the power stroke, when your exhaust valves open, pressure between the compression ring will be greater than in the combustion chamber. Your pressure here, late in the power stroke, the pressure here will be more as that of in the combustion chamber. Late in the power stroke, when the exhaust valves open, pressure between the compression ring will be greater than in the combustion chamber, and some gases will be forced back into the chamber, and some gases, because it's a passage available to you, the gap between the piston walls and the cylinder walls, and from the piston butt gap. So some of the gases will be forced back into the chamber. This is called reverse blow-by. So blow-by raises the pressure in the crankcase and contaminates the oil with fuel and exhaust gases. As much as 1% of the fuel is forced into the crankcase in some engine. To keep crankcase pressure down, it must be ventilated. So your crankcase, the lower portion, you have the engine head, then you have the engine block or engine body, and the lower portion is the crankcase or the sump. So the crankcase or the sump has to be ventilated to avoid the buildup of pressure. Because of the oil contamination caused by blow-by, oil filter system and more oil filter systems and more frequent oil changes are necessary. So one of the reasons that oil loses its property due to the blow-by, and we have to replace the oil filter and the oil in the engine. Now, the last thing, first, engine pressures as a function of crank angle showing cylinder pressure P1, pressure between piston compression rings P2, and pressure in the crankcase. There is a time delay for pressure changes from one cell chamber to the next due to the restricted flow passage past the piston. When the exhaust valves open and blowdown occurs, pressure in the combustion chamber decreases quickly, so P2 is greater than P1 can occur. This is when reverse blow-by occur. The need for crankcase ventilation can be seen by the pressure buildup in the crankcase. Now let's see the graph on the right side. We have this x-axis with the crank angle, on y-axis we have the pressure. Now at BDC, your piston is at intake stroke is finished and the piston is at BDC. Let's start moving towards TDC, the compression stroke. Piston is moving up. It is compressing the air fuel mixture. The pressure is rising. So P1 is rising, P2 is rising, P3 is rising. Now at TDC, you have the combustion, power stroke starts, and the piston starts moving towards BDC. Okay. So at the now let's see the cylinder pressure increasing. At the end of the compression stroke, we have a P1, we have a combustion, we have a maximum pressure, maximum temperature here, and the rise of pressure between the compression ring is also there because it is linked with that. And P3 is the crankcase pressure. It is very less at TDC. As the piston moves from TDC to BDC in the power stroke, the pressure the area is increasing, so pressure is dropping. And here, the pressure between the compression rings also dropping. But somewhere near when your intake valves open here, the main pressure in the combustion chamber drops quickly. But the pressure in the between the compression ring and the valves is more, and the crankcase pressure is more. So we have a reverse blow by here in this region. When we have exhaust blow down, we have a reverse blow by because P2 is greater than P1. So gases or pressure, high pressure gases will try to escape the compression ring and goes to the combustion chamber and goes to the exhaust. Okay. So this how the air fuel motion in the combustion chamber is. So with this, we comes to the end of our chapter 6. I hope you are liking my videos. So please do share